Okay, this is the overview. It actually doesn't match up with my slides very well. So a little bit of background on GSM so you guys are kind of up to speed on what's happening. Then I'm going to talk about base station and then baseband stuff and then a conclusion. Actually, yeah, ignore that slide. It's wrong. Okay. So the GSM protocol is absolutely fucking huge. It's made up in dozens and dozens of documentation. Like there are these 1,000-page PDFs that you have to read. So, for example, to understand the L1 layer, which is the radio encoding layer, you have to read a 500-page document called GSM 0508. If you want to understand how the L3, the actual application layer, works, you have to read GSM 0408, which describes the application layer. You have to read a separate GSM document which describes how the structure formats are defined, and then another one that describes how the definition of the structure formats are encoded. Right? So you need to read 3 documents just to understand it. Or you could do what I did and cheat and just read the source code to GSM implementations, as well as 0408. So basically, if you're getting into GSM, you can skip most of it and just do 0408. It's the simplest one. It helps if you have an understanding of telephony to begin with, how it's set up with basically signaling and data layers. But anyway, so at the lowest level of GSM, the actual RF part, I stole all of these pictures from Wikipedia, by the way. So like my art isn't anywhere near this good. Basically, the important thing to take away from this is that GSM is based on TDMA, which is time division multiple access. So it's all based on clock timings. The stream of bits in the air is actually decoded based on time. So you have to sync the clock in your phone to the clock in the base station correctly in order for you to be able to interpret the bits back and forth. The important thing here is that there's actually only a very, very small amount of data per time slice, per time slot. So each of these things is called TS for time slot. There's TS0 through TS7, so there's 8 of them. You pack them together and you have a frame. So 8 time slots is 1 frame. You pack those together, you can either have 26 or 50. So basically you have 27 or 51 of them in total, and those are called multi-frames. You add multi-frames together, you get super frames, which take 6 seconds to transmit. And then you add super frames together and you get hyperframes, which take 3 hours, like 3.5 hours to transmit. So the hyperframe is important for A5, which I'm not going to talk about because I don't care about it. But basically, the frame position within the hyperframe is used as part of the encryption input. So that's important for A5 stuff, but not for us. Essentially, each of these time slots has 23 bytes of information. So when we do our fuzzing attacks, when we're trying to fuzz the phone, we only have 23 bytes to play with. So we could actually do a complete exhaustion of all of the possible combinations in a very, very short space of time. It takes us, I think, 3 days to run through a complete exhaustion of just one channel. Right? Okay, so we have these 3 layers that go into GSM. Everything in GSM is it's compacted into just sets of initials. So the layers are called very creatively L1, L2, and L3. Sometimes you'll see the abbreviation L123, meaning all of them together, or L23, meaning just layer 2 and 3. Important one over here, L1, that's the lowest level, as I said before. That's slightly above the radio level. That's literally just how things are encoded in the air at the radio level. It's kind of boring. There's not a lot you can do with it security-wise. If you get it wrong, then the phone just is unable to decode the bits, or the network equipment is unable to decode the bits. Like, there's not a lot you can do there. L2 is actually quite thin. It basically determines which of the L3 state machines should receive input from the L1. So L1 decodes or encodes the data, passes it to L2, and L2 looks at it and figures out which part of L3 should handle it. Then L3 contains the application layer stuff, and that includes things like CC, MM, and RR. Right? So CC is call control. Call control is used very obviously for setting up and tearing down telephone calls, and MM is mobility management. It's basically used for authentication, and for moving from one cell to the next cell. So it deals with basically the auth part of the GSM stack. And then RR is radio resource, and it's used for dealing with opening channels and closing channels and so on. So those three things, CC, MM, RR, L123, like we've got tons of these, so everyone should keep up, right? Then we need to look at the sorts of channels that you have. So as I said, like you've got these time slices. Each time slice will be assigned to a channel, typically. So for instance, C0 TS0 is channel 0, time slot 0. That's the BCCH, it's the broadcast. So if we go through these quickly, you'll see that we've got BCCH, which is the broadcast control channel, FCCH, which is the frequency correction channel, SCH, which is the synchronization channel, and the CBCH, which is cell broadcast channel. Basically, BCCH pours out all the information about a cell. So if you're using if you have a BlackBerry and you have it set up for the engineering screen, like everyone's done that, right? You can hack your BlackBerries and like get engineering tools. If you do that, it will have a screen which lists things like all of the available ARFCNs, the available cells, and several of the timers and so on. All of that information is sent over the BCCH and sent as system information messages. So there's SI1, SI2, SI3, SI4, 5, 6, 7, 8, up through 16, but only 1 through 4 are important. And once again, we're not going to deal with those specifically. So all of these are basically broadcast channels. They're unidirectional. They only go down from the network side to the phone. Okay, so there's the downlink from the network to the phone and the uplink from the phone to the network. Most of the attacks we're going to be looking at today are uplinks, so they're from the phone to the network. They're much more interesting. All right, then we have control channels. Okay, these are actually useful for us. So there's the paging channel, the PCH. The paging channel is used to announce to a phone that there's an incoming SMS or an incoming phone call that it needs to respond to. There's the RACH, the random access channel. RACH is used by the phone to request a channel. So it sends a request up. I'll go into this in a bit more detail. So it sends a request to the network, and the network allocates a channel and sends it back down. It sends it back down on the ACGH, the access grant channel. Right? So these three are actually kind of critical for us to understand GSM. Then once you've opened a channel, you're going to get a SDCCH. It's a standalone dedicated control channel. The particular one that you have isn't really important. What's usually critical is how it gets used on the application side at the back end. So there's fast association and slow association, which are based on authentication levels, as I recall. And then this ACCH, I'm not sure what that is. Right. Now, the important thing to remember about a GSM channel is that they are fucking slow. It can take 2 to 3 seconds to open a channel. Right? They're not instantaneous because it's all based on time slots. So once you make your request, it can take a while for the backend to have a slot available where it can respond to you again. Right? There can be really, really like huge amounts of time that get wasted in there. That hurts us mostly on the fuzzing side when we're using our base station to fuzz phones, because opening a channel can take a long time. It so far hasn't been a huge issue, but it's something to be aware of. And also there's a lot of channels, right? So everyone's comfortable with that, right? Like the SDCCH, PCH, AGCH, RACH, right? L123. Yeah, we're good to go? Any questions? No? Awesome. Okay, so now we're going to look at how a channel is opened. Opening a channel is actually fairly straightforward. Okay, so the phone makes a request on the RACH, and this request is basically made up of a random 25-bit value. All right, so you can see like this is strong security at work so far. So the random 25-bit value is chosen by the phone. It sends a request to the tower. The tower will find an open channel and put that information in the access grant channel response, and it will send back a response saying the person who made request 01 now has channel, this time slice, this channel, this frequency, blah, 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 right? So that information comes back, and at that point the phone can then attempt to make the connection by using that information to transmit, right? So it's pretty much asynchronous. The phone makes a request. If it gets a response, then it can then associate on that channel. Right? All good. Okay. The other setup is, so that would be if the phone initially wants to make a call itself, if it's trying to contact the network out of nothing. If, on the other hand, there's an incoming message or incoming SMS or an incoming phone call, the tower will broadcast over the PCH. It will broadcast. The person with this ID number has to, basically should talk to me and get a channel. So it'll send a broadcast out on the PCH, and these are very, very simple. It's a 32-bit value, which is called the TMSI. It's the Temporary Mobile Subscriber Identifier. And it sends that out, and then the phone that has that TMSI will respond. And it will respond by sending an RACH, right? Gets back on the ACGH, and then you've got an LCH. Yeah? No questions? Awesome. Okay. Part of the funny stuff that happens with this is, for example, the way that older phones that didn't have a lot of memory and didn't want to generate random values or use a tick counter, they would pre-select 32 random values and burn those into the firmware. And then they would just use a pointer to iterate through those 32 values. So that's how they would get the random values for this stuff. So you do get collisions fairly frequently. Right? I mean, 255 bits is not a lot of space. Right? This is sort of what a typical cell station will look like. So the BTS is the base station system, the BSC is the base station controller, and the MST is the mobile switching center. Right? Everyone's got that? No problems. So the MS, or the mobile station, will connect to one of the ARFCNs, which is the absolute radio frequency control number, or code number. All right? This isn't too much for anyone, is it? Okay, so ARFCN is basically a specific subset of the GSM band that you're using for your communications. So of the GSM bands, which is like 850, 900, 1800, and 1900, there's actually subsets within that of 200 kilohertz, megahertz, some value that's fairly small, and those get paired together. So there's an uplink and a downlink. And then those get divided. So there's 1024 of them in total, going from 0 to 123. And there's a simple algorithm to convert from a ARFCN number to the specific frequency that you're using. And it's basically like you add 20 and multiply by, or you multiply by 20 and you add the base value or something like that. It's very, very simple. Pretty much the important takeaway from that is the low values from like 0 through, I think, 256 are GSM 850, 256 to 512 are 900, 512 up into the low 800s or so is for 1800, and then there's a crossover from 1800 to 900 where 623, which is, for example, the ARFCN my BlackBerry is on right now, 623 is either 1900 or 1800. And unfortunately for the demos over here, it's 1900. So as I mentioned, the demos don't work on 1900 band. All right, so that's at the actual tower end. So usually they'll have several ARFCNs per BSC, and those ARFCNs have very, very low levels of logic. They're not very sophisticated. All they do is the actual radio encoding and decoding, and they pass all the information back up. Then the BSC will monitor